Hi, I'm Yuxiao, a PhD student at Carnegie Mellon University. Welcome to our paper, RISE, Recursive Introspection, Teaching Foundation Model Agents How to Self-Improve. This is a joint work with Tianjun Zhang at UC Berkeley, Garg at Llama2 and Aviral Kumar at Carnegie Mellon University. We noticed that current large language models, even strong ones, often struggle to improve their responses over multiple attempts. As shown in prior work, even changed to better refinement prompt, self-correction consistently results in a decrease in performance. Our goal in this work is to develop a method to teach language models how to self-improve effectively. To give an intuitive sense of what those kind of mistakes look like, here are some examples. And after fine-tuning with RISE, the model is able to figure out the error and maintain the correct steps in previous response, and only correct the mistakes. To achieve self-improvement, several approaches have been explored. Prompting techniques like chain of thoughts and self-refine often need model-specific prompt and external feedback to maintain improvement over turns. People also tried fine-tuning on domain-specific Oracle solutions, or use multimodal systems like Glory with different models for generation, criticism, and refinement. Our new method, RISE, takes a different approach. As a single model solution, RISE doesn't need model-specific prompting and learns from both optimal and suboptimal data. Most importantly, it improves consistently with more attempts without external feedback. In addition, it can generalize to other domains, making it a versatile tool for various problems. We first convert single-term problems into a multi-term Markov decision process, where the state is user's prompt or environment's feedback. The action is the entire response generated by language models, given the complete conversation history, which includes all previous states and actions. The reward is based on the correctness of only the answer in language model's response. We then collect the data by unrolling the current model at most k-1 times in the kth iteration, and construct an improved version of the response by either sample multiple responses from the current model and use the best response, which we call self-dissolution, or create a more capable model, which we call dissolution. We can repeat this process to iteratively collect the data with more unroll steps. With the aforementioned data construction schemas, we then use reward-weighted regression for fine-tuning the model. In this process, ST, YT, and RT represent the state, action, and reward at step T, respectively. We introduce tau as a temperature parameter to further expand or narrow the difference between good and bad actions. During inference, we follow a similar schema to the data collection stage, but with two key differences. First, we don't use a stronger model to generate improved response. Second, we now don't have Oracle environment feedback. Instead, we simulate a scenario by always telling the agent that its answer is wrong. This forces the model to generate multiple responses sequentially. We then apply majority voting on the candidate outputs from different turns to determine the final response. Before we dive into the experimental results, let's address the fundamental question. Why is self-improvement over turns even possible? We identify two key reasons. First, enhanced model expressivity. By learning a sequence of conditionals, the model can represent more flexible distributions, making it easier to learn the target distribution. As shown in the figure here, training with RISE allowed the model to solve problems that even larger sampling budget at the first turn cannot solve. Second, the model implicitly instills a verification procedure into the learner. This allows it to evaluate and improve its own responses, forming a generalizable strategy that works even on out-of-distribution prompts. The broad figure shown here the model trained with problems sampled from GSAK and math, but it still maintains self-improvement ability in another environment which is ramped. Here are the results for running RISE. On common mathematical reasoning benchmark, GSMAK, RISE improved the performance of a fine-tuned Llama2 7 billion model by 17.7% over the course of 5-turn introspection. Whereas the parallel sampling with the same generalization budget at the first turn only improved the model by 50.7%. This demonstrates that after running RISE, the model can utilize information from previous attempts and achieve self-improvement. RISE can also be deployed on other models. It can improve Mistral 7 billion by 23.9% over 5-turn introspection, while parallel sampling in the first turn only improved 15.3%. Similar trends hold on math, where RISE improves the Llama2 7 billion model by 4.6% and the Mistral 7 billion model by 11.1% over 5 turns with no oracle guidance. Look for other methods like self-refine, glory. The gain are much more smaller and often negative, even when pseudo language models at the 7 billion scale are used. This demonstrating the effectiveness and the generalizability of our. Finally, I want to emphasize the key takeaway here. We can get language models to self-improve their own if we train for it properly. This is a capability that even strong proprietary models don't have, and we show it's possible to get this via RISE, which deploy an iterative RL recipe on top of unpolicy rollout data. For more details, definitely check out our project page with the link or scan the QR code and come to talk to us. Thank you. Bye-bye.